my group, we actually use a lot of ESXi servers. You would think that after using these things for 10 years, I would know how to speak, but I do not. We use these for virtualizing machines. Some of these actually run sandboxes or run kind of dubious software on it. So we really do want to prevent these processes from jumping from the virtual environment to the hypervisor environment. We have today, we have F1YYY. He wants to be known by F1YYY, so I'm respecting that. He's from Triton Security Labs, and he's going to show us how the exploits that he discovered in the, I think it was the last Chinese Geekpwn capture the flag, and he's going to show us how these things work. And with that, I'd like to ask you to help me welcome F1YYY onto the stage.
Is it? Hello? Hello. Hello? Hello. Thanks for the instruction. Good evening, everybody. I'm F1YYY, a senior security researcher at Triton Technology. I'm going to present the great escape of ESXi, breaking out of a sandbox virtual machine. We have demonstrated this full exploit chain at Geekpwn 2018. I will introduce our experience of escaping the sandbox on the ESXi. I will also introduce the work we have done about the sandbox on the ESXi. Now, let's start it. We come from the Triton Security Research Lab. We have researched many practical targets in recent years, including PS4 jailbreak, Android routing, IoT offensive research, and so on. Some of us also play CTF with Team Bloop and T-Delivers. We recently won the championship at HitCon Final. We are also the organizer of the real-world CTF. We created some very hard challenges this year. So if you are interested in it, we welcome you to participate in our CTF game. Now, before we start our journey to escaping the virtual machine, we need to figure out what virtual machine escape. I'd like to ask some of you that, did anyone use the virtualization software? If you have used the virtualization software like VMware Workstation, Hyper-V, VirtualBox, and so on, please raise your hands. Okay. Thanks. Many. So if you are a software engineer or a security researcher, you probably have used virtualization software. But if anyone has heard the word virtual machine escape, if you have heard that, please raise your hand again. Oh, surprised. Thanks. It surprised me that all of you know about that, but I have to introduce that again. What's virtual machine escape? In normal circumstances, the host OS runs on the hypervisor, and the hypervisor will handle some sensitive instructions executed by guest OS. Host OS emulates virtual hardware and handles RPC requests from the guest OS. That's the architecture of normal virtualization software. And the guest OS is isolated from each other and cannot affect the host OS. However, if there are some bugs or if there are some vulnerabilities existing in the host OS, it's possible for the guest OS to escape from the virtualization environment. They can exploit these vulnerabilities. And finally, they can execute arbitrary code on the host. So this is the virtual machine escape. Then, why we choose ESXi as our target? The first reason is we know that more and more companies are using or plan to use private cloud to store its private data, including these companies. And the vSphere is an enterprise solution offered by VMware. It's popular between companies. If you are a net manager of a company, you may know about VMware vSphere. And the ESXi is the hypervisor for VMware vSphere. So it's widely used in private cloud. That's the first reason. The second one is that it's a challenging target for us. There are several exploitations of VMware Workstation in recent years. Hackers escape from the VMware Workstation by exploiting some vulnerabilities. These vulnerabilities existing in graphic cards, network cards, and USB devices, and so on. But there has been no public escape of ESXi before. So it's a challenging target for us, and we love challenge. Then, why is ESXi so challenging? The first reason, I think, is that there are little documents about its architecture. The only thing we can find is a white paper offered by VMware. The white paper only includes some definitions and pictures without details. So let's take a brief look at the architecture of ESXi first. ESXi is an enterprise bare metal hypervisor, and it includes two parts. The kernel, it uses VM kernel developed by VMware, and the user world, and the other part, the user world. The VM kernel is a POSIX-like operating system, and it uses an in-memory file system. It means that all files stored in this file system are not persistent. And the VM kernel also manages hardware and schedules results for ESXi. VM kernel also includes VMware drivers, IO stacks, and some user words API offered to the user words. And the word user word is used by VMware to refer the processes running in VM kernel operating system. And the word user word means that a group of these processes. These processes can only use a limited proc directory and limited signals, and they can just use some of the POSIX API. For example, there are some user word processes like hostd, sshd, VMX, and so on. Then, that's the architecture of ESXi. I'd like to give you an example to show how a virtual machine works on ESXi. The VMS process in the user world can communicate with the VMware by using some undocumented, customized system call. And the VMware will initialize the environment for the guest OS. When guest OS executes some sensitive instructions, it will cause a VM exit and return to VMware. The VMS process also emulates virtual hardware and handles RPC requests from the guest. That's how a virtual machine works on ESXi. Then, how can we escape from the virtual machine on ESXi? If there is a vulnerability in the virtual hardware of the VMX, we can write a driver or write an exploit to escape from it. The driver will communicate with the virtual hardware, and it can exploit the vulnerability. And finally, we can execute shellcode in the VMS process. So it means that we successfully escaped from the virtual machine on the ESXi. So the second reason about why ESXi is so challenging is that use the word API. The VMX uses many undocumented and customized system calls. And if you want to reverse some code of VMX, it's hard for you to understand which API the VMX is using. But luckily, we found two system call tables after uncompressing the k.b00 field. There are two system call tables we found with symbols. So this field will be useful if you want to reverse some code of the VMX. This is the second reason. Thirdly, there are some security mitigations here, including ASLR and NX. It means that we may need to link some address information before we start our exploit to break the randomize of the address space. Furthermore, after testing, we found that there is another mitigation on the ESXi. There is a sandbox. There is a sandbox isolates the VMS process. So even you can execute some shellcode in the VMS process, you cannot execute any commands. You cannot read any sensitive fields unless you escape from the sandbox either. And finally, we think that the VMS of ESXi has a smaller attack surface. After comparison of the VMS binary between the workstation and the ESXi, we found that there are some functions have been removed from the VMS in the user world to the VM kernel. For example, the packet transmission function in E1000 net card has been moved from the VMX to the VM kernel. And if you have read some security adversaries published by VMware recently, you can notice that there are many vulnerabilities existing in the packet transmission part of E1000 net card. And all these vulnerabilities only affect workstation. So we think that the VMS of ESXi has a smaller attack surface. Now, let's start the journey of escaping from the ESXi. Let's overview the entire exploit chain first. We use two memory corruption vulnerabilities in our exploit. The first one is an uninitialized stack usage vulnerability, which CVE number is CVE 2018-6981. And the second is an uninitialized stack read vulnerability, and the CVE number is CVE 2018-6982. And we can do arbitrary address free by using the first vulnerability. And we can get information linkage from the second one. After combining of these two vulnerabilities, we can do arbitrary shellcode execution in VMS process. And finally, we use a logic vulnerability to escape the sandbox of VMS and reverse a root shell from the ESXi. So that's the entire exploit chain we use. Now, let's start the first one. The first vulnerability is an uninitialized stack usage vulnerability. It exists in VMS necessary net card. When VMS necessary net card tries to execute command update MAC filters, it will use a structure on the stack, the physics memory page structure. This structure is used to represent the memory mapping between the guest and the host. And it's also be used to transport data between the guest and the host. Then, the VMN net will call function DMA create to initialize the structure on the stack first. Then, it will use this structure to execute this command. And finally, it uses physics memory release to destroy the structure, the physical memory page structure. So it seems that there are no problems here. But if we look at the function DMA memory create, we can notice that there is a check before the initialization of the physics memory page structure. It will check the argument address and the argument size, and if the check passes, then it will initialize the structure. But if the check fails, it will never initialize the structure on the stack. And finally, we found that we can control the address argument by writing a value to one of the registers of VMS net3. What's worse is that in function physics memory release, there is no check about if the physics memory page structure has been initialized, and it's just free a pointer of this structure. So let's think about it. If we can pad the data on the stack, it's possible for us to do arbitrary address free. We can pad a fake physics memory page structure on the stack, and then make the check fields in the function DMA memory create. And finally, when it comes to the physics memory release, it will free a pointer of our physics memory page structure. So we just tried to find a function to pad the data on the stack. There is a design pattern in software development. We will store the data into the stack if the size is small when we allocate some memory. And otherwise, we will put it into the heap. And we find a function that fits this pattern. This function will be used when our guest OS executes the instruction out_sb. It will check the size. If the size is smaller than 0x8000, it will use the stack to store the data. And finally, it will copy the data we send from the guest into the stack. So we can use this function to pad the data on the stack. Then, how do we combine this to do arbitrary address free? We can use out_sb instruction in guest OS first to pad the data on the stack. This data should contain a fake physics memory page structure. And the page count of this fixed structure should be 0, and the page area of this fake physics memory page structure should be the address we want to free. Then we set some registers of the VMS net3 to make the check fields in the function DMA memory create. And finally, we order the VMS net3 net card, execute the command update MAC filters, and then in the VMX, it will use the physics memory release to destroy the structure we pad before. This structure is the fake structure we pad in the first step. And it will check the page count. If it's 0, it will free the page area of this fake structure. So we can do arbitrary address free now by using the first uninitialized stack usage vulnerability. Here comes the next one. The second vulnerability also exists in the VMS net3 net card. When VMS net3 net card tries to execute command get policy, it will first get a lines from the guest, and the lines must be 16. Then it initializes the first 8 bytes of a structure on the stack. But it just forgets to initialize the next 8 bytes of this structure and just write this structure back to our guest OS. So we can link 8 bytes uninitialized data on the stack from the host to our guest. And after debugging the VMS process, we realize that there are fixed offsets between the images. So it's possible for us to get all the all the information about the address space by using this vulnerability. Now, what do we have now? We can do arbitrary address free by using the first one, and we can get all information about the address space by using the second one.